Hi students, now in this video lecture we will go through order of crystallization, then some properties of some salts, delinquescence, efflorescence and hygroscopy. Okay, before this we are already aware of saturated solution. What a saturated solution is, you take, let's suppose you take water, you add sodium chloride to it, it will dissolve, right? Add more sodium chloride to it, stir it, it will dissolve. Keep adding sodium chloride to it or any other salt for whichever salt you are preparing saturated solution. Till one point of time it will keep dissolving, then a point will come when at that particular temperature at which you are preparing that solution, the solute, that is the sodium chloride that we are adding to water, will stop dissolving, right? No matter how hard you stir it, it won't dissolve at that particular temperature, right? So at that point the solution is known as a saturated solution, when the solution can no more dissolve the solute, right, that we are adding. So suppose we prepare, now let's take an example of a solution of copper sulfate, right? We prepare the solution of copper sulfate at 80 degrees Celsius, right? What we do is we add copper sulfate to it, right, and we'll prepare a saturated solution of copper sulfate. Once you get a saturated solution, that is, once you reach at a point when no more of a solute is getting dissolved, right, at that point of time just filter the solution, right, and then allow the filtrate. That is, you filter this solution using a filter paper, right, and what comes out of the filter paper, right, is a filtrate, right, that contains dissolved copper sulfate. That filtrate contains dissolved copper sulfate, right? And when you allow that hot concentrated solution, or when you allow that hot saturated solution of copper sulfate to cool, when you allow it to cool, right, after some time, say after a day or half a day, you will notice crystals of copper sulfate that will settle down at the bottom of the beaker or the container, right? So this is known as the process of crystallization. What is the process of crystallization? Process by which crystals are obtained by cooling a hot saturated solution, right? We prepared a hot saturated solution, right, filtered it, right, and then we cooled the filtrate, right, and after some time we noticed crystals settle down at the bottom of the beaker, right? This is known as process of crystallization, right? Now the crystals that are formed, there are two types of crystals that we get using crystallization, right? One form of crystal will have, when crystals will form, right, one form of crystals will have some water molecules, right, attached to it or associated to the crystals. In the crystals you will have some water that is associated to the crystal, right? Then there are other types of solutions or the other types of crystals. For example, if in a similar way we prepare a saturated solution of sodium chloride, right, and in a similar way if we cool, right, if we cool this hot saturated solution of sodium chloride, we'll get crystals of sodium chloride, right? So in case of copper sulfate, the crystals of copper sulfate will have some water molecules associated with it, whereas in case of sodium chloride, the crystals of sodium chloride would not have any water associated with it, right? So you get two types of crystals when you do crystallization. One is that have water, right, other is those that does not have water, right? Now these crystals that have water, are called hydrated crystals. These are hydrated crystals, and these that does not have water, these are anhydrous crystals. Right. An example of hydrated crystal is copper sulfate, right? And since I said it, these salts that are crystals that are hydrated crystals, they have some water molecules associated to it. They have some water molecules within their crystal structure, right? So we write it as like this. It has 5 molecules of water associated with it. Similarly, if we talk about sodium chloride does not have any water molecules associated with it, and we call it as anhydrous, that is without water, right? Now, water of crystallization, I explained you so that we can understand what is water of crystallization. To this water molecule that are associated with copper sulfate, these water molecules are known as water of crystallization, right? Or we also call it as water of hydration. These water molecules are called water of crystallization or water of hydration, right? These water molecules are loosely bonded to the crystals of copper sulfate, right? By loosely bonded we mean if we heat it to a temperature of 100 degrees Celsius, these water molecules will get removed from these crystals of copper sulfate, right? So I'll also write it here, they are loosely bonded, right? So how do we define water of crystallization? The fixed amount of water that is associated with hydrated crystals, which is integral part of the crystal, right? The fixed amount of water that is associated here. What is the fixed amount of water? 5 molecules of water are associated with copper sulfate crystals, right? So 5 water molecules is called as the water of crystallization or water of hydration. The fixed amount of water that is associated, right, with the hydrated crystals, right? And it's an integral part. These water molecules are integral parts of the crystals. And what are hydrated and anhydrous salts? These are hydrated salts that has water molecules associated with it, and those that do not have water molecules associated with it are called anhydrous substances. Substances which contain water molecules along with salts like sodium carbonate or copper sulfate, right? We have studied this. And substances which do not contain any water along with salts are anhydrous substances, example sodium chloride and potassium nitrate. And some more examples of hydrated crystals if we take, we have Epsom salt, magnesium chloride 7H2O, right? We have Na2CO3.10H2O, sodium carbonate, we has 10 water molecules that are associated with it, right? Similarly, if you make crystals of magnesium sulfate, it will have these number of water molecules, 7 water molecules associated with it. So all these crystals are called hydrated crystals, and the water molecules that are associated with it, we call it as water of crystallization or water of hydration, right? Now, how to prove what is the effect of heat? How to prove that all these crystals contain water of crystallization, right? We'll do a simple experiment, right? We'll take this, test tube, right? And when heated, right, here you have these crystals. We have crystals of copper sulfate, right? When you heat it slowly at the cooler parts of the test tube, it's a cooler part, at cooler parts you will see some water droplets, at cooler parts of the test tube you will see some water droplets, right. So this proves that this salt, copper sulfate salt or crystalline salt, right, crystals of copper sulfate contains water molecules, and these water molecules are what you see that deposits at the cooler parts of the test tube, right. These water droplets that you see at the cooler parts of the test tube are due to the water of crystallization, or the water molecules that are associated with copper sulfate, and we've already said that these are loosely bonded, right. That is why when we heated the crystals of copper sulfate, these water molecules easily got removed from these crystals, right. So copper sulfate dot 5H2O I'll write it over here. So copper sulfate dot 5H2O when heated, right, it will change into copper sulfate plus 5H2O, and these water droplets that you see at the cooler parts of the test tube. So now, due to this associated water molecules, the color of copper sulfate was blue. These were blue crystals, right. And this, when heated, it changed into this copper sulfate, which is anhydrous, right, and it will change into an amorphous form. It will change into anhydrous and amorphous form. Anhydrous means without water. Since water is removed from copper sulfate pentahydrate, we call it as copper, we name it as copper sulfate pentahydrate. Water is removed, so this is copper sulfate pentahydrate, we got it copper sulfate anhydrous and amorphous. Anhydrous means without water, amorphous means without crystalline shape, that is in the powdered form, right. This is a powdered form, right. And if you add water to this anhydrous and amorphous form, it will change back to the blue crystals. This reaction can occur in the reverse direction as well. I'll repeat, when you heat the blue crystals of copper sulfate, it will change into white anhydrous and amorphous. These are white anhydrous, that is without water, and amorphous, that is without crystalline shape, right, without crystalline shape and in a powdered form, right. And if you add water to these anhydrous and amorphous powdered form of copper sulfate, this powdered form will change back to blue crystals of copper sulfate, right. Now let's understand what is the effect of heat on sodium chloride, which is a anhydrous crystal. So when you heat sodium, we take some sodium chloride in a test tube, right, start heating it. If you take some sodium chloride in a test tube and you heat it, right. After a time, you will start hearing a crackling sound as if something is cracking, right. That crackling sound came due to these bigger crystals breaking down into smaller ones, right. And this crackling sound is known as disreputation, right. This crackling sound is known as disreputation. I'll write it over here. Disreputation, right. I'll repeat, when you heat the anhydrous sodium chloride in a test tube, you will hear a crackling sound, right, and that crackling sound is known as disreputation, right. And the reason for that crackling sound is when bigger crystals of sodium chloride are dissociating or breaking down into smaller crystals, right. Bigger crystals breaking down into smaller ones produce a crackling sound known as disreputation, right. So remember what is disreputation and what is the effect of heat on anhydrous salts. right? You can just take down everything. I'll pause the video and just take down all the notes. Right, now we have something known as efflorescence, deliquescence, and hygroscopy. Now, what is efflorescence? Efflorescence is, suppose you have sodium carbonate crystals, right? If you leave crystals of sodium carbonate in air, right? If you leave in open air, right? Then after some time you see that the crystals, right? Crystals of copper sulfate, crystals of sodium carbonate will lose its water molecules that are associated with it, right? And will change into a powdery form. It will change into an amorphous form, which is a powdered form. So sodium carbonate that has 10 water molecules associated with it, right? And these water molecules we have studied as is called as water of crystallization or water of hydration, right? When they are left in air, say they are left in dry air, right? These decahydrate crystals will change into monohydrate, right? 9 water molecules were removed from these sodium carbonate crystals and only one molecule of water is left. So this is a monohydrate plus 9H2, and this would be a powdered form, right? We also call it as amorphous form. This phenomena is known as of efflorescence. That is, when hydrated crystals are left in air, they will lose their water of crystallization and changed into this powdered form, right? This is known as efflorescence. Similarly, if you leave sodium sulfate in air, which is again a decahydrate, it will change into sodium sulfate without any water molecule. In dry air, this will also change into sodium sulfate plus 10H2. All water molecules are removed, are lost, right? So these kind of salts, this phenomenon is known as efflorescence, right? Similarly, and one more thing, since suppose we have these sodium sulfate crystals, right? This is kept in a container in air, right? We know that air also has some water vapor in it, right? And this salt, sodium sulfate salt, also has water in it, right? So these water will have some vapor pressure, since this is water in it, right? Water vapor. So these water molecules will also will have some vapor pressure, right? This will have some good vapor pressure, and since this is kept in air, so air will also have some vapor pressure that it will exert on this salt, right? This is air vapor pressure, and this is salt vapor pressure. Why salt vapor pressure? Due to these water molecules that are present in the salt. So this water molecules that is contained in the salt will also have some vapor pressure. And this phenomena of efflorescence, that is losing these water molecules, will occur only when the vapor pressure in air is less, right? When this vapor pressure that is exerted on this salt is less, right, compared to the vapor pressure of this salt, right, then only it will lose its water molecules, right? So we write salt vapor pressure, right, should be greater than because you can just imagine or just think in your brain, when the vapor pressure that is due to this salt is more. I'll just make big arrows to show you this. When this vapor pressure is more, then only these water molecules will leave this salt, right? Because if suppose the vapor pressure of air is high, right, compared to the salt, right, suppose these are very high, right, it won't let these water molecules from this salt to get removed from the salt, right, since it will exert a higher pressure, so it won't lose these associated water molecules. So we say salt vapor pressure should be greater than air vapor pressure, right, for efflorescence. And when will this happen? Salt vapor pressure would be greater than air vapor pressure, right? This will happen in dry condition, when vapor pressure in air, when this vapor pressure in air is less, and this would be less in dry condition, in dry air. So air should be dry. To favor the process of efflorescence, the air should be dry. Then only these salts will easily lose their water of crystallization, right? So salt vapor pressure should be greater than air vapor pressure for efflorescence, and this will happen in dry air, right? This will happen in dry air. So phenomena of efflorescence will get promoted in dry air, right? So this is little, you need to understand this, that vapor pressure of salt should be greater than the air vapor pressure for efflorescence, right? You can remember these things from these arrows. When the vapor pressure is high of the salt, it will lose these water molecules, right? And this will happen in dry conditions, because in air vapor pressure would be less in dry conditions, right? So just remember this. Now we have a similar process, deliquescence, right? Deliquescence is exactly opposite of efflorescence. In efflorescence, what happened? This salt lost its water of crystallization. This salt is losing water molecules to air, right? Now there are certain salts like sodium hydroxide, or certain compounds like sodium hydroxide, potassium hydroxide, magnesium chloride. These salts, when left